Let us start Module 10, Chapter 5. In this module also we continue our study of topologies in the function space y to the power x. We have studied pointwise convergency topology, topology of compact convergency, and also topology of uniform convergency. If we minutely note that, we can observe that in case of topology of compact convergency and uniform convergency, in both cases the space X has been considered as metric spaces. Whether we can remove the metrizability of X, we shall investigate this in this module. There is a topology called compact open topology where we can remove the metrizability condition. When we put the metrizability condition, we shall observe that this compact open topology will coincide with topology of compact convergency. Let us go to slide presentation. As I have told in the introductory discussion that we have observed that both the uniform topology and compact convergency topology made specific use of the metric D for the space Y. Now we are going to investigate whether we can remove the metrizability condition from Y. Though we are unable to give any satisfactory answer, but for the subspace Cxy, that is the set of all continuous functions from x to y, one can provide some partial results. It turns out that there is a topology called compact open topology which coincides with compact convergency topology when Y is a metric space. This topology is also important in its own right. So, let us start with the definition of the compact open topology. Let X and Y be two topological spaces. If C is a compact subset of X and V is an open subset of Y, let us define SCU is equal to all continuous functions from x to y such that f of C is contained in U. Then it can be proved that the sets SCU form a subbasis for some topology on the set of all continuous functions from x to y. This topology is called compact open topology. By definition, it is clear that compact open topology is finer than topology of pointwise convergency. In fact, in the topology of pointwise convergency, it has been used the compact sets as singleton. Though the compact open topology is defined on the entire space y to the power x, but it is only of interest in case of continuous functions from x to y. So, whenever we speak about compact open topology, we shall always consider it only on the space of all continuous functions from x to y. Let us first examine equivalence of compact open topology and topology of compact convergency when one space is metric space. As we have discussed in the introduction, this is expected that compact open topology and topology of compact convergency should coincide when Y is metric space. Let YD be a metric space. On the set CXY, the compact open topology and topology of compact convergency are equivalent. That means whenever Y is a metric space, if we consider compact open topology on the space of all continuous functions from x to y, then that is equivalent with the topology of compact convergency. To prove this theorem, for a compact subset A, let us define the set U A epsilon as the set of all those points which are less than epsilon distance from A. Now, let A be a compact set and V be an open set containing A. As we know that in a Hausdorff space, compact sets always behaves like point. In this way, we can say that there exists some positive number epsilon such that A is contained, U A epsilon is contained in V. Indeed, if we set epsilon is equal to infimum of d of A x minus V such that A belongs to capital A, then the above holds. From now, we shall call U A epsilon as epsilon neighborhood of capital A, where A is a compact subset. First, we wish to prove that compact open topology is contained in the topology of compact convergency. That is, topology of compact convergency is finer than compact open topology. To prove this, we have to show that if we take an open set in compact open topology, that is also open set in the topology of compact convergency. That means if we take a open set in the compact open topology and take a member of this, we have to find an open set of topology of compact convergency containing that point and contained in that open set. For this, let U be an open set in capital Y and C be a compact set in capital X, so that SCU be a subbasis element of the compact open topology on CXY. Now, let small f be a member of SCU. We have to find an open set of the topology of compact convergency which contains F and contained in SCU. Now, as F is continuous and continuous image of compact sets is always continuous, we have that FC is a compact subset of the open set U. So, by our notation, there exists some positive number epsilon such that the epsilon neighborhood of FC lies in V. That is, U of FC epsilon is contained in V. This of course implies that BCF epsilon is contained in SCU, but F belongs to BCF epsilon. Hence, we have found an open set of topology of compact convergency within F and SCU. That means topology of compact convergency is finer than compact open topology. Now, to prove the converse part, that is compact open topology is finer than topology of compact convergency, let us choose some continuous functions from x to y. Then for any open neighborhood W of f in the topology of compact convergency, there exists some positive real number epsilon such that f belongs to BCF epsilon, which is contained in W. To complete the proof, we shall find a basis element for the compact open topology that contains f and lies in BCF epsilon. Now, for each point x of capital X, let us choose Vx such that f of Vx lies in the epsilon by 4 neighborhood of Fx. That is, Vx is a neighborhood of x which is mapped by f to the epsilon by 4 neighborhood of Fx. Then f of Vx bar lies in epsilon by 3 neighborhood of Fx, which has diameter at most 2 epsilon by 3. Let it be Ux. Now, the collection Vx such that x belongs to C is a cover of capital C, and C being compact, there exists a finite subcover. So, we can choose x1, x2, xn such that C is contained in union of Vxi, I is equal to 1 to n. Let Cx is equal to Vx closure intersection C, then Cx is compact being intersection of two compact sets, and the basis element SCx1 Ux1 intersection SCx2 Ux2 intersection up to SCxn intersection Uxn contains F and lies in BCF epsilon, which is our required point. So, this proves that compact open topology is finer than topology of compact convergency, and therefore, these two topologies are equivalent whenever X is a metric space. Now, if we observe the proof of the above theorem closely, we can observe that the metrizability of Y is required, but there is no role of the particular metric on Y. So, we have the following theorem. Let Y be a metric space, then the compact convergency topology on Cxy does not depend on the metric of Y. Therefore, if X is compact, the uniform topology on Cxy does not depend on the metric of y. So far, we have introduced in this module the compact open topology on the set Cxy, that is the set of all continuous functions from x to y, and we have shown that if y is a metric space, then the compact open topology on Cxy and topology of compact convergency are equivalent. We have also shown that these two topologies does not depend on the specific metric on y, it only depends on the metrizability of y. So, if x is compact, then the uniform topology on Cxy also does not depend on the metric of y. Let us pass to the slide for some other applications of compact topology. Let us state an important property of compact open topology for locally compact spaces. If Y be a locally compact Hausdorff space, then the mapping capital F from Cxy Cartesian product Cyz to Cxz defined by f of small f g is equal to g compose f is continuous, where all the spaces are endowed with compact open topology. That means given a function f from x to y which is continuous and a continuous function g from y to z, the composite function g compose f is in Cxz. Now, if we consider an open set containing g compose f in Cxz, we have to find an open set containing f in Cxy in the compact open topology and an open set in Cyz in compact open topology containing G such that the Cartesian product of these two open sets goes by F to the open set containing G compose F. So, let U be an open set in Z and C be a compact subset of X and G compose F belongs to SCU. That means we have taken an open set containing G compose F. Now, since G compose F belongs to SCU, therefore, by the definition of SCU, we have that G compose F of C is contained in U. That is, F of C is contained in G inverse U. Now, since F is continuous and capital C is compact, F of capital C is compact. As we know that in compact Hausdorff space, compact set always can be considered as point. So f of C can be considered as a point in the space capital Y. Again, as Y is locally compact Hausdorff space, there exists an open set V in Y such that f of C is contained in V, is contained in V of closure, is contained in G inverse U. Here closure of V is taken in capital Y. Now SCV is an open set in the compact open topology in CXY, and SV bar U is an open set in the compact open topology in CYZ, whose Cartesian product contains FG. Now it can be easily proved that capital F of this Cartesian product is contained in SCU. Hence, we have proved that there exists an open set containing F, G, which is mapped by capital F in a neighborhood of G compose F. That means capital F is continuous. For locally compact space, we also have the following theorem. Let capital X be a locally compact Hausdorff space and CXY have the compact open topology. Then the evaluation map E from X Cartesian product CXY to capital Y defined by EXF is equal to Fx is continuous. The mapping E is called evaluation map. So, to prove that E is the continuous function, let us take a point xf of X Cartesian product Cxy. Then Exf is equal to f of x. Now let V be an open set containing x in capital Y. We like to find an open set containing xf which will be mapped by E into V. Let us first use the continuity of f. Since f is continuous, there exists an open set containing x in capital X which is mapped by small f into capital V. But capital X is locally compact Hausdorff. That means we can take the compact closure of U in place of U. That is, we can take a compact neighborhood, say U bar of X, such that f of U bar is contained in V. Then consider the open set U Cartesian product S of U bar V in capital X Cartesian product Cxy. It is an open neighborhood of the point xf, and if x dot f dot belongs to this set, then Ex dot f dot is equal to f dot of x dot, which also belongs to V as desired. Hence, we have proved that there exists an open set containing the point xf which is mapped by the evaluation map E into V. Therefore, E is continuous. So, in this module we have discussed compact open topology in details. We have given some application of compact open topology for locally compact spaces also. With this we end this module. Let us pass to next module.